This Chem Catalyst video is on VSEPR and molecular shape. If you look at this Lewis structure for NH3, you can see that it's limited in what it tells us about the molecule. It obviously tells us some good information. It shows us how the hydrogens are linked to the nitrogen, which is the central atom. It shows us our bonding electrons, and it shows us also our non-bonding electrons. But what it doesn't show you is this molecule's actual three-dimensional shape. It's like I've taken this molecule and I've squished it flat into the plane of this paper. Now, quick point here, if you don't know how to draw Lewis structures, you want to look at one of my other videos, which is drawing Lewis structures using the need-have-share method. But assuming that you know how to draw Lewis structures and you want to figure out molecular shape, you can continue on with this video. Molecular shape is important because it has a huge influence on the properties of a molecule. The model that we use to determine shape is this model that's called VSEPR, and this stands for valence. So you can think about valence, that's outermost electrons, and obviously that would be S stands for shell. So the valence shell, or the outermost electron, and the P stands for pair, and the last thing stands for repulsion. So if I draw my Lewis structure for NH3 here, the way that I've drawn it, I've kind of applied VSEPR to some degree because I've shown these electrons as repelling each other. Notice like this is about as far apart from that. These non-bonding electrons are about as far from those bonding electrons as I've got down here and down here. But again, the challenge with this is that it's restricted into the 2D flat plane that I'm drawing on here. So what I want to be able to do using this model is actually extend this into 3 dimensions. So there are a couple basic shapes that we need to know when we are looking at VSEPR. And these are for fairly simple molecules. And here are the shapes that you can see right here. The shapes are linear, and you can see in a linear molecule that the atoms themselves are 180 degrees apart from each other because the electrons have repelled themselves as far apart as they can go. Another shape that we have is bent, and there's actually 2 ways that you could produce a bent shape. One, if you have sort of a 1 non-bonding pair of electrons and 2 bonding pair of electrons, and notice that would produce a bond angle of 120 degrees. Or if you have 2 bonding pairs of electrons and 2 non-bonding pairs of electrons. So a couple examples of these, or one primary example, is water. Water has the Lewis structure of HOH, like that. And if you looked at this in paper, you might want to think that water is actually linear, but that's not the case, because when you expand this into 3 dimensions, you can see that the electron geometry happens to be tetrahedral down here. You can see that. And then the bonding pairs make it have a bent shape. Now, I introduced a term there where I talked about electron geometry or electron shape, or molecular geometry. The molecular geometry only includes these bonding pairs. All right, but the electron geometry includes all of the pairs of electrons. So this molecule actually has tetrahedral electron geometry, but its molecular geometry is going to be bent. So down here we have the situation where we've got trigonoplanar. Now you can think about trigonoplanar molecule. One example is actually the nitrate anion. Nitrate looks like this. And again, there's 3 resonance forms for it. I don't have time to draw them all right now, but to properly do this, nitrate is NO3 minus, so I'm going to put a minus on here, and note that I should draw all the resonance forms, but I can't fit them in. But you can see here that that these bonds would be 120 degrees apart from each other, and they would all be in one plane, because that's the farthest that these valence shell electrons can repel each other. right? Tetrahedral over here, a common example is methane, which is CH4. CH4 is pretty simple here. You're going to have all of your bonding electrons form 4 bonds between hydrogen and carbon, and they would repel each other to be 109.5 degrees. And then the example that we use at the very beginning, this is actually a NH3 molecule, where you would have your lone pair electrons up here, and you would have a primary bond angle of about 109.5. It actually would be less than 109.5 because these non-bonding electrons kind of cause this angle to distort, so it's a little bit less than 109.5. So these are the primary shapes that we are going to be dealing with when we're looking at valence shell electron pair repulsion. We're going to look at linear molecules, bent molecules, trigonal planar molecules, trigonal pyramidal molecules, and tetrahedral molecules. So for today's chem check, what I would like you to do is take a look at this problem, go ahead and solve it on a separate sheet of paper, press pause first, and then go ahead and check in for the solution. So the electron geometry for this molecule is going to be determined by its Lewis structure, and the Lewis structure for this molecule looks like this, H2Cl. So if I want to know electron geometry, the electron geometry is going to be trigonal planar. The molecular geometry, again, now there's no lone pair electrons to consider here, so the molecular geometry is just going to be trigonal pyramidal as well. Sorry, trigonal planar. And the bond angles would be 120 degrees, because that's as far as these electrons could repel each other.